This video is going to cover thermal deformation. Thermal deformation is another type of axial deformation, except it's changed due to temperature. So it's effectively the same dude. We start off with del, because again, he has deformation, and he has axial deformation, but he's due to temperature, so we give him a little t. His equation's really simple. It's alpha times delta t times L. And what these things are is alpha is a coefficient of thermal expansion. And this is, again, it's just a material property. So all you have to do is just go look it up online. Technically, with our book, you can technically find the values in the textbook, the ones that obviously we're using the Hibbler book, so Hibbler will have his values that he wants you to use. But in general, they may have a little bit of a range, but I'm going to go Google because that's what I do. Delta T is the change in temperature. And again, a positive change in temperature is a temperature increase, and a negative change in temperature is a temperature decrease. And L, again, is the original length. Now, the reason that I did make sure to tell you and specify that this is an axial deformation is because of length, right? The original length is the axial direction. So it is down the axis of the member. That would be like normal force direction. So it is important to make sure that that is the length you are getting, not like a width or anything like that. So this really isn't a complicated equation. As far as units go, it's 1 over degrees whatever. I'm going to use Fahrenheit because I'm going to be doing US customary units. It'd be degrees Celsius if you're in SI units. Temperature, again, in either degrees Fahrenheit or degrees Celsius. And my length, I'm going to make sure is in inches. So that means my deformation is in inches. All right, so they're very simple units. And now we're going to pop into an example. So for this example, let's just say we have this steel rod, and this steel rod has a diameter of 10 inches, very not to scale. It sticks out 4 feet, and on the end of it, we put a 10 kip load. It's also outside, go figure, and therefore there's a change in temperature of a drop of 25 degrees Fahrenheit. So we had a change of negative 25 degrees Fahrenheit. We want to find the total axial deformation, and to do that, we need to find the axial deformation due to the load and the temperature and add them together. Because they're all axial deformations, we can do this. So again, our load one would be P times L over A times E. So there's a few things of information that we do need. We have P. P is in blue, right? There is P. We have L. L is in purple here. There's L. A, well, technically we have a diameter, so we can find that. But E, where is E? E comes from steel, so maybe we need to go Google that. So we're going to Google that E for steel is 29,000 KSI. Our next equation that we're going to have is the temperature one, which again is alpha times the change in temperature times the length. Now again, we already have the length. The length was in purple. Delta T was given to us, so delta T is right there. So lastly, what we do need is alpha. And again, it's a material property, so we can look that up online. And we're going to find 6.5 times 10 to the negative 6, 1 over degrees Fahrenheit. It's kind of really important that you actually get the right one, right? Fahrenheit is what we use for US customary. Celsius is what we use for SI units. Do make sure you are not messing that up. Technically, as long as the temperature change you were given is going to cancel, it's not going to be an issue, but it would be really tragic if you put the wrong number in there. So definitely do pay attention to your units when doing this stuff. So now that we have that information, let's go ahead and find our deformation due to load first. So load, again, P. P was 10 kips. Is it positive or negative? This is pulling. Pulling is going to be putting our bar into tension, and tension is going to be positive, so this is a positive 10 kips. Times the length. The length we have 4 feet. Now, we never actually do area or modulus of elasticity in terms of feet, and nobody wants deformation in terms of feet either. So make sure you're converting out of feet back into inches. So there we go, we have 12 inches in a foot divided by the area, which we have a diameter, so we can calculate an area. That's going to be pi divided by 4 times d, which is 10 inches squared. And lastly, E, let's go ahead and just stick that in red over here. He is 29,000 KSI. So ta-da, not anything new, not anything difficult here. We're going to get positive 0.000211 inches. Okay, that's load, that wasn't temperature, so that's nothing new. Now we're going to do the deformation due to temp. And the temp one's really simple, right? We have alpha. Let's give alpha a new color. How about green? So alpha here, 6.5 times 10 to the negative 6, 1 over degrees Fahrenheit. We had a change in temperature of minus 25, so he needs a new color. He'll be light blue because he's getting chilly. So minus 25 degrees Fahrenheit. And then our length, and again, our length was in purple, and our length was 4 feet. But if you put this as 4 feet, yes, your degrees Fahrenheit are going to cancel here, but then you're going to get deformation in terms of feet, and that's a little bit stupid. So don't forget to turn that into inches. So there's 12 inches in a foot. Ta-da! Now we're actually gonna get our deflection due to temperature. And since we do have a minus for the temperature, right, that minus sign right there does mean we are going to have a minus for our deformation. And that's 0.0078 inches. Now, so that's actually quite significantly different compared to that 10 kips of force. So just getting colder by 25 degrees Fahrenheit, which isn't actually too unfounded if you just think about a regular day. There's just like a regular day's worth of temperature change right there. And this thing's only 4 feet long and it's made of steel. Like, it's going to shrink way more than that force. So yep, 10 kips doesn't actually create that much deformation. So the total, again, all we have to do is sum them together. For load, it's positive 0.000211 in inches. And then we have to add in our temperature, but our temperature is negative 0.0078 inches. So so our total deformation, including our temperature, is going to mean that we're going to have a negative 0.00759 inches. So yep, actually temperature controlled in this itty bitty easy little example.